Hi, my name is Melanie Beechwood. I'm a master's student with Curry College at Northeastern University. This is my final project presentation for computer vision in spring 2026. I'll be going over Monocular Visual SLAM using OpenCV today. So let's go into a little bit more about what this means. First off, SLAM is simultaneous location and mapping, which means that it's going to get a live feed that gets both the location where the camera is in the world and the 3D map of the world updating simultaneously. You can see a version of it over on the right. That is an image pulled from the tutorial I'm following, where you can see that the point cloud is creating that 3D mapping of the world, and that green trajectory line is the camera's location within it. Monocular vision just means that there is only one normal RGB, oops, sorry about the spelling mistake there, camera in use. So this is not a stereo system, and this isn't using any other sensors, it's just one normal camera. For any of my live videos, this was with my iPhone 1X, so it's primary camera on the... So I did this following a tutorial on OpenCV. The link is in the reference as throughout. This combo from the Mono SLAM paper and Orb SLAM, but customizing it to be focused on a beginner. So Monocular Visual SLAM is a more simplistic way of doing it, which is nice when you're a beginner, but the overall reason for a Visual SLAM can be robots, autonomous vehicles, including things like a moon or a Mars rover, and 3D mapping of different places. You see this a lot with LiDAR and other sensors and stereo, where the monocular vision is a little bit more simplistic, but does have some downsides. All right, so here is a diagram from the tutorial, kind of going through what we're going over. For the input, we're going to be getting image frames. Since this is a monocular system, we are going to be doing this over a time t, so seeing the difference between two frames instead of between two stereo systems. We'll also be getting our intrinsic matrix K, either from our calibration file. In this case, I'm using the one that we did in Project 4, that's the calibration system that we designed, or from the tutorial where they give the matrix itself, and you can put it in either way. The first step in this pipeline is to do feature extraction. This is very similar to what we did in the last project around finding interesting features. And in that project, we used Harris corners. This is using a slightly different corner algorithm, and we're using an OpenCV method to detect those features. And also we're going to be playing feature tracking a little bit here too. Next up is feature matching, where we will be using, so also between the feature extraction and feature matching, we'll be using Orb, and then BF Matcher as another OpenCV matching algorithm. In this case, we're going to be using a Hamming distance on it because the Orb is a binary descriptor instead of vector. Once we have the matching of which features are the same between the two, that's when we now have basically those two frames, and we can do a camera pose estimation and triangulation. And then lastly, we're going to be bringing all of those points that we have found and putting them up on a 3D map and building that world as we go. This tutorial is going to stop here. These are considered the front-end algorithms of a modern SLAM system, but it does keep going as far as description, and for the future work, this is where I'd be going. So the next step would be bundle adjustment, where this is finding similar points and bringing them together, as far as I understand, and then loop closure, which figures out if you've seen that spot before, and then finally pose graph optimization. So to start off with, I went for an initial understanding. So I did a first pass through the tutorial, trying to do each stage from scratch as I got to it, so without reading ahead. There was a little bit of code snippets, so a little bit like a Jupyter notebook style, but in just a Python script. In this, I explored bringing that calibration in, doing live instead of video like they had, doing feature extraction with Orb, feature tracking with optical flow, feature matching with BFM Matcher, using that Hamming distance, and then some pose estimation and triangulation. At that point, you could get some of it, but the full end-to-end wasn't working since their tutorial left a few things out, which is my only critique of this particular tutorial, is it did make it difficult to do that versus it kind of is split into these kind of two natural ways of doing it, but it was really fun to get to do. Over on the right, the top image is what it looked like at the feature matching state. You can see how it's picking up information on the printer, the words on the page that just got printed. And then one of the ones I thought was really interesting is that it really likes catching my wallpaper on my office. The one in the middle is actually the feature tracking with an optical flow. So you can see an example of a medium movement on the left, where you can see the red being where the current frame is, with that green showing that distance moved between the two frames. And then on the right is an example of a large movement. Object tracking, as we talked about in class, does struggle with large motion, and you can really see that here, where some of it was able to capture it, and then other times it kind of just goes all over the place. And then on the bottom is an example of the feature matching, where it took those points from the image up at the top across two frames, and then found the ones that were most similar using a K and N with just a 2, and then it didn't do any further ranking that I will end up doing in the next stage, but just from that it's able to do a pretty good job about finding it. You can kind of see the strings as they go across. The next step of my methodology was to go deeper. This was using the code that they provided, but introducing my own calibration files, a few more options, and the ability to go live, things that we've done throughout the semester. The biggest jump here, and why I didn't end up doing any other novel work, was because I had to rewrite the display that they used. They were using a 3D pangolin renderer that did not work on my Mac. I couldn't get it to install properly due to being on an M. There was a more direct port that would have been a bit easier with OpenCV, but I also online could not get that one on the M1 either. So that was left with me translating it into Matplotlib. I don't have an extensive history with these kind of rendering, and this is my first time in a 3D point cloud. So having to change this and knowing whether I changed anything in the algorithm at the same time didn't make any sense. So I kept their code almost identical, as identical as I could. And the goal from this point on was to see if I could match their output and really get this running. And then kind of experimenting. Over on the right, you have one of my experiments. Thank you, Professor Maxwell, for helping me kind of figure out how to best visualize this when I didn't have that 3D renderer to mimic them, and what to do to help me figure out if it's working correctly. So this particular one was from a example that I did within my office, where I held my phone in my arm fully outstretched to help stabilize it, and then moved my body to make an arc in a counterclockwise direction with my phone camera pointing out. That's what that little triangle is supposed to represent. This is a small idea of kind of the features that it would have seen, and the point cloud that it generated underneath. The green line is the trajectory, with the blue being where the camera was at the end. I was really happy to see that the direction of the arc did match up. The point cloud did make sense with what I was seeing in the live video, and that helped make it more assured. Another experiment I did was in a bar. This is kind of a funny place to be for this, but I found it was really interesting because of all the feature tracking from the bottles. On the left is one of the last frames from it with that feature tracking feature extraction on it. So you can kind of see what the movement was on that frame. And then on the right is the localization and mapping. The way that room was set up, that big gap is actually expected. There was a very blank wall with almost no features on it, so that was expected. What was unexpected is that in the bottom right corner you can see a little tail stick out. That was developed at actually right about this frame. These started appearing, and that's behind the camera. I was not able to track down why it was putting it as behind the camera, but because I didn't see that behavior in other environments like the one you saw before, I'm suspicious it's something within this environment. I'm curious, since it seems like it's picking up a lot of the reflection points on that back tile, if there's something with that seems to be throwing it off or not, because it doesn't start doing that until we get into that reflection spot. All right, the biggest experiment though was to mimic the tutorials. They had 3 videos that they provided and a few GIFs on their site to get an idea. The other critique of this particular tutorial was that there actually wasn't a lot of ways to kind of check your work. So this was the best one I could find. I got the same video and processed it to the same frame point, or as close as I could. The image on the left is from one of the final frames in that, not in the video, but from where I stopped it to match where the GIF on their website on the tutorial shows. This is from mine, so this is an annotated frame with that feature tracking to give a little bit more interest and kind of see what it's looking at. The image in the middle is theirs, so this is with the Pangolin 3D renderer. It is at a small perspective shift as best I can tell, and then it does have a much lighter red than I chose to do with mine, but you can see the trajectory there and that cloud. And then on the right is my output with a top down, so the perspective is slightly different. And then because I just used a red point cloud instead of a more transparent one, it is quite a bit more dense. Now, some things that you can notice that gave me concern is that right to the bottom left of my trajectory, there's a bunch of points. Those start appearing right around at this last frame. At first, I was concerned because I was seeing it here as I was seeing in the bar, but then I noticed in theirs it's harder to see because of how faded it is, but it is appearing in theirs as well. This leads me to think that this is not a problem with how I did my visualization, but because we haven't implemented those back-end algorithms yet, but I would have to get to that future work to find out. I was happy to see though that their GIF is cut off so you can't see the further outliers, but for the clusters that are closer, they look fairly similar, which is promising to me. So in conclusion, I was able to match the tutorial output. The anomalies seem to be very similar. This does run real time on my MacBook. I can use my own calibration and a live camera or use theirs, or a different calibration file and a video. I definitely started understanding it more, and when doing the related works, I found that there's over 40 years of work, including large published surveys covering other large surveys of different techniques. So there's so much to learn here. For future work, I would love to go further into implementing. They do have some offline style backends like in Jupyter notebooks where you can do a more computationally intensive bundle adjustment, keyframe, and loop closure, and I'd really like to stripe that and then move towards one of these more modern methods such as Orb Slam, either 2 or 3, and get that live. It would also be really cool to play with either the stereo or the RGB depth variants. I've already got this textbook, Introduction to Visual Slam from Theory to Practice, which I'm really excited to learn more about this space. And I have definitely realized doing this that it is beyond time that I have a linear algebra course, and I could really use a little bit more understanding around that and the geometry to get a better sense, especially when going deeper into these algorithms. All right, I do have a quick live demo for you all. This is going to be with that tutorial, or that Ohio one. Let me rearrange everybody a little bit. I didn't put any images, but I did also do a 3D perspective, again in Matplotlib, which has kind of that similar perspective that they did, along with the top-down and a front that's not useful in this particular video. This is about where the GIF stops, but I'm going to let this run for just a little bit longer so you can kind of see it. There is more errors the longer it goes, but I think it is really interesting to see how it is correctly getting the depth a lot closer to this, but it is catching some of those trees and some of those far along features, and we can kind of see those in the sparse that is further back there. All right, I'm going to go ahead and stop that. There is references. If you're curious, these are all the references I used in my project. There's a lot of really good reads here if you want to go in further. Thank you very much. Bye.